All right, welcome back, everyone. Today we're going to be talking about the antiderivative. Now, the antiderivative is probably the second most important part of what you learn in this calculus class, um, where the goal of taking the derivative of a function was our initial uh, goal in this class. If you were given a function like f of x equals 3x squared, we now have learned many techniques to actually find the derivative f prime. We know that by the power rule this is going to be 6x. Now the antiderivative is the opposite operation. So if you're given 6x, how can you get back 3x squared? Now for a function as simple as this, you could do it without even thinking. You know that um, if you think about what values of x and exponents and leading coefficient will give you back, uh, will give you 6x when you take the derivative, then you'll be able to do it. But there are functions that are way more complicated than this, and it does become very difficult to actually start guessing. Um, so that is basically the motivation of what an antiderivative is. Now, typically, you do the following. Suppose that somebody on the train tells you um, to find some function f. This function we're going to denote by using capital F, and the derivative of f is given by little f, which is 3x squared. Okay, so this is basically, going from this one and finding what came before it. Okay, now again, from our knowledge of derivatives, we can say, hey, I know a function that I've seen where when we take the derivative, we get back 3x squared. That function is x cubed, because when you take the derivative of x cubed, if you do, d dx of x cubed, the derivative of this is 3x squared, right? So this function f is called an antiderivative. So t. Now notice that I'm saying the word and not the antiderivative. The reason for this is, as we will see after I write this definition, is because uh, these antiderivatives are not unique. So let's see. Let me write down this definition. So a function f, capital F, is an antiderivative of little f on an interval I if the derivative of capital F of x is equal to f of x, little f of x, for all x's in I, in the interval I. So basically, what this is saying is that the derivative of capital F is equal to this little f. Much like here, the derivative of this capital F is 3x squared, but that was our little f. Okay? Right, now, like I just mentioned, this capital F we call an antiderivative rather than the antiderivative. And to see why, we simply need to look at the following. Let me call this function f1, and f of x1 is equal to x cubed. Is the first one we had. Now capital F2 is going to be equal to x cubed minus 5, and let's do one more. F3 is going to be equal to x cubed plus 97. If we take the derivative of f1, then f prime of x, again, is going to be simply equal to 3x squared, just as before. Now the derivative of f2 of x is going to be equal to 3x squared plus 0, because the derivative of negative 5 is 0, so that's just 3x squared. And the derivative of this f3 of x is also going to be equal to 3x squared, because again the derivative of 97 is just 0. So notice that if we have if we are adding or subtracting a constant to our derivative, then we just get back the same derivative. You know, f prime of 1 is equal to f prime of 2 is equal to f prime of 3. But these are not the same. These do not come from the same antiderivative. So what I'm saying here is that the antiderivative of f1 prime of f prime 1 is this right here, and the antiderivative of this function is this one. Notice that they're not equal, but their derivatives is. That's why we do not say the antiderivative, because there are infinitely many antiderivatives that give us the same derivative function. Notice that I have 3 different functions and they all give me the same derivative. That's because I'm adding by a constant. So this leads us to the following theorem that says if f, capital F, is an antiderivative of little f on an interval I, then capital G is an antiderivative of f of little f on the interval I, if and only if G is of the following form. G is of the form G of x is equal to capital F of x plus C for all x's in the interval I, and C is a constant. So notice that if we go back to this example that I just did, this is true. The g's that I have are antiderivatives, because notice that we have f of x. So what was my f of x here? My original one was x cubed. So all of them have an x cubed plus or minus a constant, plus or minus a c. So this is f of x minus c. This one is f of x plus c. And by this definition, by this theorem, G is an antiderivative because it's of that form, f of x plus a constant. We will do many examples of this, and you'll eventually be able to see exactly what I'm talking about. Now, there are some rules that I will be bringing up. Much like with the derivative, there are many rules for the antiderivative, most of which you will cover in Calculus 2. In Calculus 1, we will focus mostly on something called U substitution that we will do near the end of the course. Calculus 2 is fully devoted to solving antiderivatives, or finding antiderivatives and so on. Now, before I move on, I want to really quickly define one more thing. So what I'm going to define for those of you who are going to be math majors, you will deal with this in a class called ordinary, and it's two classes. One is ordinary differential equations, the other one is partial differential equations. If you go to our textbook has a small section about differential equations, so I just want to talk a little bit about them. So a differential equation is simply an equation that involves x, y, and derivatives of y. Okay. For example, what is a differential equation? And a differential equation would simply be y prime equals 3x, or like y prime equals, let's say, x squared plus 1. These are examples of differential equations. Now you could have differential equations of multiple variables, not just of x, but of x and y at the same time. Okay. Now, if you were to find let's say somebody came up to you in the train and told you find the, let's say, general equation of, let's say, y prime equals 2, then what we're looking for is, this is the little f of x. So we're looking for an antiderivative of this. So we're looking for capital f of x. So we're looking for a function whose derivative is 2. And a simple function whose derivative is 2 is simply 2x, because remember, when you take the derivative of 2x, you just get back 2. But by the previous theorem that we just wrote, we know that this right here is what we call an antiderivative. It's just 1. To get the general solution, we could write the function g of x. So we could say a more general solution of this will be the following. We could write, I'll do it in blue. We could write g of x is equal to f of x plus c, where c is a constant, right, by definition, by the theorem. And then we just substitute. What is f of x? F of x is 2x, so this is just g of x equals to 2x plus c. Okay, so this is a general solution for the differential y prime equals 2. Okay, so if somebody gives you an equation that is in the form of a derivative, then that is a differential equation. It's in the name. Like if somebody comes up to you in the train or the bus, like, you know, in the Bronx that happens a lot. You go to the bus and somebody goes in and they give you something like, you know, dy dx is equal to 3x plus 5. So if they give you something like this, now you know that this is called a differential equation. And we've been dealing with them for a while, because this is just the derivative of some function. You know, you could find a function whose derivative is this. In fact, we could do that now. What would that function look like? That function will look like 3x squared over 2 plus 5x plus some constants if you want to make it the general one. This is definitely going to give you this, because if you take the derivative, notice that when the 2 comes down, they're going to cancel out. You minus 1, so you get 3x, and then the derivative of 5x is just 5. Okay? Now, let's talk a little bit about notation for the antiderivatives, because this is going to be very important. Sometimes you see this in graffitis in the Bronx or in New York City. You know, I've seen it in Brooklyn, I've seen it in Manhattan. A lot of graffiti artists love to do this. I'm being very sarcastic right now. Well, first of all, when solving a differential equation, of the form, much like I had it up there, dy dx equals little f of x, it is useful to write it in its equivalent form. So it is useful to rewrite it as the following. Simply cross multiply. You know, we have dy dx equals little f of x, technically over 1. So what we're really doing is kind of cross multiplying. So you have dy dx on one side and f of x dx on the other side. So this is a very conventional notation for a differential equation. Now, the process of actually finding the solutions of this equation is called, anti-differentiation, or a new word that you probably have never heard, indefinite integration. So the process of finding the general solutions of this equation is called anti-differentiation, or indefinite integration. Why does it get also the name indefinite integration? Because of the symbol that we use, which is called the integral sign. So this process is denoted by the integral sign. Which looks like this. Okay. Now the general solution, we write it like this. So we will have something like y is equal to the integral, this is how you read it, the integral of f of x dx, and that is going to be equal to capital F of x plus c, which is basically what we had before, but now we're using the notation. So again, this is the integral sign. This middle piece right here, where your function is called the integrand. Okay. This piece right here, the dx, tells you what the variable of integration is. You could have dy, you could have du, you could have dv. It just tells you could have d theta. It just tells you what variable you're integrating with respect to. Capital F of x is what we know as the antiderivative, much like before. And this c is just a constant of integration. We always have to add a constant because, as we saw from the first few examples, there are an infinite amount of antiderivatives for the function f of x. Okay? So let me just say one more thing and end this part of the video. So this expression, you just write it, this expression f of x dx is read as the antiderivative of f with respect to x. Sometimes you also hear the integral, so also you may hear it as You may read it as the integral of f with respect to x. You will hear both. So this is what we call the antiderivative. It is the opposite operation of the derivative. Much like if you think about adding, the opposite operation of adding 2 to a number is to subtract 2. The opposite operation of multiplication by, let's say, 2 is to divide by 2. So if you have something like 5 plus 2, you get 7. If you want to undo that and get back to 5, what do? You have to subtract 2 from 7. Similarly, when you multiply, let's say 5 times 2, you get 10. If you want to go back to where you began, back to 5, what do? You have to divide by 2. So it undoes the multiplication. With derivatives, we spent I would say 3/4 of the class talking about how to take derivatives, and that gave us newer functions. We began with a function, we took the derivative, we ended up with another function. But if we want to go back to our original function, we have to find the antiderivative or an antiderivative of the derivative that we have, or the new function that we had. This is going to be extremely important in the next couple of lectures for sure. And if you plan on taking Calculus 2, then the whole Calculus 2 class is spent talking about the antiderivative. It is assuming Calculus 2 that you already know every single rule of taking derivatives. So when we come back in the next part of this lecture, we'll do a bunch of examples of how to take antiderivatives.